Okay, so the discussion for today is a handful of family of operators, namely the trace class and the Hilbert-Schmidt operators. So just to establish some notation that we're going to be using a lot, H is going to denote a Hilbert space. And if you see two brackets like this will denote an inner product. Normally, I won't have that subscript H in there, but for the conventions that we're going to be using here, just remember that we're using an inner product that's linear in the first entry and conjugate linear or antilinear in the second entry. The letters xc and eta will be vectors in H. And then I will denote by theta sub xc eta the rank 1 operator defined by the following formula. Just to remind you all what these Greek letters are, xc, eta, and zeta. I have them written on screen here. Um, then we'll let FR of H be the collection of all finite rank operators, which you can think of as the span of the operators I have up above. K of H is the set of compact operators, and you can think of that as the norm closure of the finite rank operators. Okay, so some abbreviations that I will be using. ONB is an abbreviation for orthonormal basis for your Hilbert space H. And PSD sometimes refers to positive semi-definites. Usually this means positive semi-definite operator, which I will remind you, it really just means that this is non-negative for all XC in H. So this is the meaning of X is PSD. Okay, with that out of the way, let's just look at some finite dimensional stuff. So we have this object called the trace on matrices. And so if I take a matrix and I look at its entries, the trace of that operator is the sum of the entries along the diagonal. Now there's another way to write this. If you start with the standard orthonormal basis for the Hilbert space Cn, in this case, EI is the vector that's 0 everywhere, except it has a 1 in the ith location. Then the ijth entry of a matrix is given by the inner product that you see at the bottom of your screen here. X applied to the ith basis vector, then take the inner product of that result with the jth basis vector. And this allows us to rewrite this expression for the trace using an orthonormal basis. In this case, it'll be the sum of x applied to the ith orthonormal basis vector. Then you take the inner product of that value against the ith orthonormal basis vector, and then you sum all of these values. And it's an exercise in linear algebra to show that if you pick a different orthonormal basis, one that's not to the standard basis, you still get the same result. The trace doesn't really care what basis you are using. You can compute it in any way, shape, or form. So this is a calculation that you should be able to work out. And a similar exercise, let's say you take a projection onto some subspace of Cn. Now let's make sure that's a projection here means orthonormal projection. Then the trace of that projection is the same thing as the dimension onto which it projects. Well, this is not too hard to verify. So a few questions that we might think about is like, how could we extend this notion of a trace to infinite dimensional Hilbert spaces? Well, nice thing about infinite dimensional Hilbert spaces is that they have a orthonormal basis. So we might try to copy something like this, where instead of choosing just, a finite basis in a finite dimensional space, we just pick an orthonormal basis and we see if the sum makes sense. That leads us to the next question: what kind of issues might arise? And anytime you're taking infinite sums, the questions you should ask are, well, does this infinite sum converge? So those are the main issues that are going to arise. Now, if you think back a little bit to your analysis classes, the way you handled convergence is first you dealt with absolute convergence and then you kind of generalize from there. And so we're going to take that a similar approach here. So let's start with a simple approach to extending this notion of a trace to operators on V of H, where H is no longer finite dimension. So if X is a positive semi-definite operator, then again, I'm just reminding you its definition that it has the property that the inner product of X applied to a vector and against that same vector is always non-negative. Uh, that's hopefully what's written up. Now, let me change this up just to make things a little bit nicer. If you start with an orthonormal basis for your Hilbert space, and X is a positive semi-definite operator, this thing that I'm calling the trace of X is going to be something that I can compute. And you should be able to show that under these assumptions, the trace of X, as I've defined it here, is non-negative, potentially infinite. And on top of that, it is going to give you the same value regardless of what orthonormal basis you are using. So pick a different orthonormal basis. Um, this may be at the very beginning a slightly different formula, but it's going to give you the same value in the end. Okay, so it's sort of emulating what we've seen in the finite dimensional setting. Now, the issue is, again, convergence, things that are potentially infinite dimensional. Okay, so let's start off with the calculation just to get a taste of what this looks like. So we start with the finite dimensional subspace, and X, I'm just going to let this be the projection onto K. And so my claim is that the trace of X, again, is the dimension of that subspace. Okay, so the explanation here, walk through the following steps. Since we know that this formula trace, as I find it here, X applied to a basis vector, inner product against basis vector, sum up all those values, is independent of my choice of orthonormal basis. Let's pick a good orthonormal basis. So the first thing I'm going to do is that I know that I'm starting with some finite dimensional subspace of H. So I'm going to start off by picking an orthonormal basis of K. I may have said H earlier, I meant K. So it's finite dimensional, so it's going to let D be that dimension, and the orthonormal basis for K is going to have D vectors, all of length 1, all of which are all vectors which are pairwise orthogonal to one another. Now what I'm going to do is I'm going to extend E0 to something I'm going to call E. This is just going to be a completed orthonormal basis for H. So add more vectors until you have a basis for H. And using these choices, there is a way of expressing this projection onto K as a sum of rank 1 operators, namely this expression that's at the very bottom of the screen. It's worth checking this. And now just a calculation that I'm going to use a lot. If you pick a vector from this orthonormal basis for H, let's just apply one of these rank 1 operators. A short calculation will show you that either you are going to get XCI back, and that's going to happen exactly when the input is XCI, or it's going to be 0 otherwise. So all you're really using is the orthonormal relations here. So let's try to compute the trace of X. Well, it is the sum of X applied to your basis vector, take the inner product against that same basis vector, take the sum over all basis vectors in E. Okay, now let's just write out what the definition of X is. All right, and now we have this expression here, and using the calculation up above, I'm going to ask the following question. What survives? Basically, what is non-zero? The only thing that's going to survive here are terms of the form xci, xci. So a lot of these things are going to be zero, and the only thing you're going to pick up are those elements of your basis vectors coming from the smaller basis for k. And now all of these things are vectors of length 1, and D here was defined to be the dimension of k. And so that's basically the full calculation that you need. And you can go back to this problem and you can check that this doesn't really depend on finite dimensionality. It just sort of made my life a little bit easier. The claim that I have here that if you start with a subspace of H, the trace of the orthogonal projection onto K is going to be exactly the same as the dimension of that subspace. So finite dimension, so they're going to be finite or infinite, and the trace will tell you exactly that. Okay, so I've started off by defining the trace on positive semi-definite things. It could potentially take on infinite values. So how do I take the trace of, let's say, potentially general operators that I might? Well, I have convergence issues, so I'm not going to be able to do this in full generality necessarily. So I'm going to have to restrict to some sub-collection where that gets some notion of convergence. Okay, so with that in mind, I'm going to start with an operator in B of H. The absolute value of that operator is defined to be the square root of x star x. This requires a little bit of calculations from the other lectures. Just know that the absolute value of x is uniquely defined. This is an operator in B of H, and it's going to be positive semi-definite. You don't really need too much more than that. Okay? We'll say an operator is called trace class if the trace of the absolute value of x gives you a finite value. L1 of B of H is going to be the set of all trace class operators, and then I'm going to denote the one norm of my operator to be the trace of the absolute value of x. Okay, now whenever x is trace class, I'm going to define the trace of x to be this expression at the very bottom of the screen. No absolute values required here. Yeah. And the idea is that since whenever I have some, trace class operator here, what I'm really looking at when I'm considering the trace of the absolute value of x here is I'm looking at the trace of something that's like positive semi-definite. And what that's going to do for me is that this expression here will be absolutely convergent, and therefore this will give me a meaningful value. Okay, so just kind of summarize those, and I have this get in this remark. Set of trace class is analogous to like absolutely summable series. If X is an L1 of B of H and E is an orthonormal basis, then this expression here converges absolutely. And although that requires a little bit more, it requires the inequality that's written here. This justifies what I said earlier, that the fact that you're dealing with something trace class means that you get an absolutely convergent sum here, which gives you a meaningful value. Saying that one more time. And another note that the dimension of your Hilbert space is finite. You have a finite dimensional Hilbert space if and only if L1 of B of H is exactly all of B of H. So in particular, When your ambient Hilbert space is infinite dimensional, L1 of B of H is a strictly smaller subcollection of B of H. In fact, you can show that the identity is an element that's not in L1 if and only if the dimension of H is infinite. So let's justify this notation L1 a little bit. So let's look at a more complex computation. Pick your favorite sequence in L1. I don't know, something like 1 over n squared. You can pick that one if you'd like. Next, pick H, a separable infinite dimensional Hilbert space. There's a lot of those, so just any Hilbert space that's infinite dimensional with countable bases. And I'm going to pick an orthonormal basis. Any orthonormal basis will do. Now I'm going to set X to be this following sum. It's these rank 1 operators multiplied by each of which are scaled by this factor a sub n. So before we move on, why are the coefficients a sub n necessary? And a following question, why is X in B of H? I will encourage you to just ponder these questions. These two questions aren't necessarily independent. All right, so this will be an operator in B of H, and my claim is that even better, it's an example of L1 of B of H, of an element of an L1 of B of H. Now, to show this, you need a couple of calculations, which I'm going to just briefly sweep under the rug. If you wanted to write x star x, you kind of take a guess and you say, okay, what would be the adjoint of x? I would probably be taking complex conjugate somewhere. Okay, now that I've reasoned that out, x star x, I multiply those things. I'm going to use a little bit of the distributive property, maybe take advantage of the fact that I'm dealing with an orthonormal basis, play around with some orthogonality relations, and lo and behold, x star x is just the same thing, but with the modulus of my coefficients squared. So it's not too hard to reason that out, but it's kind of messy to check, and I'm going to try to avoid unnecessary messy calculations because we got plenty of messy ones to deal with. Okay, now that I've reasoned out what x star x is, I might have to take a guess at what the absolute value of x is. Now, one thing that one could guess is that the absolute value of x could just be given by looking at the absolute value of the coefficients, and you'd be correct. And the way to verify this is to check that squaring this yields x star x. Earlier, I mentioned that the absolute value is uniquely computable. So once you have verified this, you know that you have the absolute value. These are the steps that you would go through. Okay, so absorbing those details, verifying them later, let's compute the trace. All right, so I have an orthonormal basis already. It's written at the very top of the screen. So let's compute the trace of the absolute value of x relative to this orthonormal basis. Okay, so just formally, here's the definition. X applied to a basis vector, inner product basis vector, take the sum. Okay, now I'm going to introduce the definition of x, of absolute value of x. Oh, God. Okay, computed absolute value of x a second ago. So let's plop that expression right on in using a couple of different letters here and there. Now over here, I'm going to take advantage of my orthogonality relations, right? And because I'm working with an orthonormal basis, a lot of these terms will be 0 unless they're not. And the only time when they're not zero is when the input matches the, uh, I don't know, I guess this subscript down here. So that cleans up this expression a lot, makes this next line a little bit easier. So then working through this, let's factor out these coefficients, and now we're left with the inner product of an against an, but that's going to be 1 since I've started with an orthonormal basis. And so all I really have is the sum as n ranges from 1 to infinity of a sub n. And that is exactly the one norm of this sequence that I had started with. Now, if we go back to the very beginning, we said that this was a sequence that was in L1, which justifies this conclusion that, hey, whatever this calculation results in, it's going to be finite. So, as a conclusion, I've justified the first thing. This is a trace class operator. Now, you can go through this whole calculation again without any absolute values and just show that the trace of x is the sum of these number of this of the terms of the sequence an. So basically the value of the series. Okay. And again, this is kind of a absolute convergence implies conditional convergence type result. So that's your first calculation for trace class. Let's just summarize a few facts about trace class operators. This is contained in theorem 8.25 in our preliminary notes. Okay, the setting is as follows. Start with a Hilbert space. The set of trace class operators is a normed space. In fact, the one norm, as we defined it earlier, is a norm, and it satisfies the following conditions. The one norm of an adjoint of a trace of a element, the trace class, is the same thing as the one norm of the original elements. The operator norm of an element is dominated by the one norm of that element. And then this other result that the absolute value of the trace of x is subordinate to the one norm of x is also true. Next, if we mix and match elements, some from B of H, some which are trace class in the following order, A, X, B, the one norm of that product is less than or equal to the product of the operator norms of A and B and the one norm of X. So in particular, if X is trace class, then all of this is finite. Or actually, the one norm of AXB is finite. So summarizing what that means, the set of trace class operators is a not necessarily norm closed two-sided ideal. And it behaves a lot like the trace on finite dimensions, which sort of allows you to swap the inputs. So the trace of AX is equal to the trace of X times A, where X is in L1 and A is in B of H. I want you to kind of notice that we have to pick elements from two different spaces. We'll deal with that a little bit later. Now, L1 of B of H with the one norm is a complete normed star algebra. So with this norm, it is a Banach space. It is an algebra because it is a two-sided ideal. So the product of elements in L1 of B of H will again be in L1 of B of H. And on top of that, I know examples of elements which are in there. For example, the finite rank elements not only live inside of the trace class operators, but they're also norm 1 dense. So if the compact operators are the finite ranks closed in the operator norm, then the trace class operators are the finite ranks closed in in this one norm. And as a corollary, L1 sits inside of the compacts. So in our notes, we don't prove this. In fact, it requires a little bit more technology than we have at the moment, but it's worth having these results at the ready. Okay, so if there's an L1, that implies the existence of an L2 and potentially an LP, but we're going to stop at 2. So an operator in B of H is called a Hilbert-Schmidt operator if the trace of x star x is finite. Think of this as saying is the trace of a function squared. If think of this as saying is that the integral of a function squared is finite. We're going to define the 2 norm of that operator to be the square root of the previous value that we computed. And we'll collect all of those with a finite 2 norm and into one collection. And these will be our Hilbert-Schmidt operators. I could define this another way. An element is Hilbert-Schmidt if and only if x star x is trace class. I advise you to check that. Depending on what resource you are using, the set of Hilbert-Schmidt operators may be denoted as L2 of B of H. That's not the only thing they can be that they can be. That's not the only notation for the Hilbert-Schmidt. I'm going to talk about another notation. A short computation shows that if you have an element that is trace class, then it's automatically Hilbert-Schmidt. Requires a couple of the facts from the previous slide, but it's not too hard to show that. So in particular, all trace class operators are Hilbert-Schmidt, and moreover, there's a comparison between the 2 norm of an operator and the 1 norm of the operator as defined relative to this trace. So one last calculation that I might get lost in, so please bear with me for 1 second. All right. So pick pick 2 n tuples of vectors in H, and just form this finite rank operator that's written on your screen here. So my claim is that the 2 norm of this is given by this expression, and this expression can be readily identified with the norm of the vectors of the norm of this vector, not sure how to say this, the sum of the tensor products of xcj, eta j bar. Viewed inside of the tensor product of H with its conjugate Hilbert space. If this part doesn't mean a lot to you, let's just verify this. All right, so to see this, start with an orthonormal basis. One of the benefits of working with the orthonormal basis is that if I wanted to write any vector relative as a linear combination relative to that orthonormal basis, all I got to do is take an inner product. What inner product? The one that I see here. Okay, so with that in mind, let's compute. All right, if I wanted to, I'm going to take a square root at the very end. So let's start by squaring everything because it just makes the calculations a bit nicer. So let's look at the 2 norm of x. Again, by definition, squared. It's the trace of x star x, which is the sum over that this expression of the trace relative to this basis. Now what we're going to do is we're going to take this x star x and just shuffle the x star over to the other side. And now we have something that's a little more manageable. Okay. First thing I'm going to do is I'm going to look at the definition of x. All right, then this is a shorthand for a rank one operator. So what we're going to do is we're going to write out what that expression means. And now a lot of things here are scalars. So we're going to be pulling scalars around in various ways. So what I'm going to do is I'm going to crisscross a few of these terms. I'm going to pull this sum out. Sorry. I'm going to pull this sum out. And when I do that, I'm going to be left. Actually, let me explain this a little bit differently. So what I have underlined here in blue is a constant. And this constant can then come out of this sum. Let me add one additional line just to clarify what I'm going to do. All right, so just duplicated that line. Now the first thing that I'm going to do is I'm going to take this sum, these coefficients, and move them outside. And while I'm at it, I'm going to do the same thing with this other sum. Uh, Great. All right, next thing that I'm going to do, I'm going to commute these sums past each other. And since these are both running to starting at the same place, ending at the same place, I'm just going to collect those. Now, what I'm going to do is I'm going to put the terms that are underlined in blue at the very end. C eta j. Then the terms underlined in purple, I'm going to put those at the end as well. And then the only thing that's left are these terms, and I'm going to put those out front. All right, so I believe all of those calculations are correct. They are not, because I need to take a complex conjugate here and a complex conjugate here. Fortunately, I can rewrite all of that by just swapping the entries here. Great. Then what I'm going to do, again, I'm going to take the same expression, I'm going to duplicate it. I'm going to take this part here Since that's just a constant, I'm going to move it into the first entry. Let's just rewrite this a little bit differently for clarity. All right, now that I'm done doing that, I'm going to take that, duplicate this, and manipulate this expression one more time. I'm going to move this sum into the inner product. Now, if you stare at this expression on its own, you can kind of look back to the very top where I made this note. That's an expression I can rewrite in a much simpler form. Let's remove all the colors since they are no longer necessary. This expression is just a complicated way of writing eta. I said eta sub k, eta sub j. Cool. And now if we stop right here, we look back to where we started. Hey, it's exactly the expression that I had before. I's and j's replaced with j's and k's, but the meaning of these two expressions is exactly the same. All right. Oh, so sometimes these calculations are a bit messy, but they're fairly manageable. Okay, let's just go back and just look at the Hilbert-Schmidt operators kind of globally rather than look through the calculations. So theorem 8.29 just summarizes a handful of facts about the Hilbert-Schmidt operators. Start with a Hilbert space. On this Hilbert space, the 2 norm is in fact a norm, and it satisfies the following comparison. The operator norm is dominated above by the 2 norm, and the 2 norm of the adjoint of an operator is the exact same thing as 2 norm of that operator. If you take a product of the form AXB and you consider the 2 norm of that, then that is less than or equal to the operator norm of A, the operator norm of B, and the 2 norm of X product form whenever X is a Hilbert-Schmidt operator. And as a consequence, this tells you that the collection of Hilbert-Schmidt operators is a not necessarily closed two-sided ideal of B of H. Now here I should say norm closed. If X and Y are Hilbert-Schmidt operators, then the product of X and Y, regardless of which way you do it, X times Y or Y times X is a trace class operator. And on top of that, the trace of xy is the trace of yx. Okay? The trace satisfies the trace property, which allows you to interchange the order, cyclically permute the order of the entries. Moreover, H, the set of Hilbert-Schmidt operators on its own, is a Hilbert space. It's a Hilbert space of operators, and the inner product is given by the trace of y star x. This will make it linear in the first entry and conjugate linear in the second entry. The set of finite rank operators on H is a norm-to-dense subspace of the Hilbert-Schmidt operators. And Hilbert-Schmidt operators can be identified with the tensor product of H with its